So here's the code that we're looking at the shortest path application. We create a flight, has from and to vertex and distance. When we construct a flight, we just set up from and to and distance. Getter, setters, from, to, and distance. Here, compare to, this is a key that whenever you insert this into PriorityQ, it's going to subtract. Right? And let's look at the shorter is better, right? Because it's shortest path. Now, this passing in this distance subtract from the other. When we start to use the graph, create that flight, and we just create two of them, flight and save flight. Saving flight is used on the PriorityQ. Mean distance and new distance. Variables to use, we create a PriorityQ, which is a heap. Set the size of the vertex to 20. For your assignment, you may not want to limit, right, the nodes. You have to be careful when using that. We create vertex, right, variables. Create a vertex Q. Create all the marks on the graph. To see is not never visit, right? Now start to create flight, save flight. Okay, equal to save flight for saving on PriorityQ. So create that first flight is Washington to Washington. So that's why start vertex to start vertex. And keep distance to 0. So it's going to print out, right, that title. We enqueue that save flight. So the first one is enqueue, which is Washington to Washington. This is going to be in the PriorityQ. Now, again, PriorityQ is going to look at compare to, right? When you enqueue. So we start to DQ. So we DQ, we get a flight which is Washington flight out. And if it's not marked, so we mark it. Right? Flight get to vertex. This one we're going to get to Washington back. Right? Because we passed Washington in here. And get to, right? From here, get to vertex. Pretty much just get to Washington back. So, is it marked? Of course not. Then we mark it as we visit Washington to Washington. And then we print the flight. So that's called toString of the flight. Pretty much Washington, Washington, and distance 0. That's why the first row is coming out like that. Okay, we switch back after we print out information. Set from vertex. Get to vertex. So now we have Washington again. Right? Get to is Washington and set from. So we have the from vertex as Washington. Get distance, which is mean distance 0. Get to vertices. This is from the graph. Get all the adjacencies from Washington. So we have return Q's. So it should return our adjacencies of Washington. Right, if you look at our it should be Atlanta and Dallas. So Atlanta and Dallas is in the queue, vertex queue. That's why we create a queue for that. Jansen's. Now, while the vertex queue is not empty because we have neighbors, then it's going to keep doing DQ. Right, DQ. So DQ first gonna get Dallas. So if it's market, no, never visit, right? Then we get the mean distance. You may see that it's actually first get Atlanta because Atlanta get in the queue first and then Dallas. So start to do Atlanta first, 600. See, so we in here, new distance. You have to accumulating it with the mean, which is starting from 0, plus wage is from Washington to Atlanta. Then you create a new flight, right? Washington to Atlanta, and then NQ to the flight. So now you have another, pretty much this one in the queue. We already DQ'd that Washington to Washington, but we have Washington Atlanta and Washington. Since it's not ending the queue yet, the queue is not empty. Right, let's go back to the loop and do another one, which is Washington to Dallas, and get the distance and return the accumulating distance with a new flight. Now queue is empty, right? Queue is empty. I mean, I'm talking about vertex queues, not the priority queue. Vertex queue is empty. So we go back to, if it priority queue is empty, no, because we have 2 more flights in there. Those have Washington to Atlanta and Washington to Dallas. So we DQ. We DQ Washington to Atlanta. And now we mark, right? If it's not marked, flight, then we mark Atlanta. And we print information, so that information print out. Washington Atlanta 600 because we print the flight information. Now we just say get to vertex Atlanta now as a new from vertex, and then we just do the same, get a distance 600 as the mean distance, and then we NQ all the neighbors of the Atlanta. So if you look back, 600 is our mean queue, in mean distance. Neighbor of Atlanta is Houston. So we create another vertex queue. It's the same. It was empty when we was using them all. Now we NQ that vertex queue with Houston. So Houston is getting in the vertex queue. We did DQ it down, and since it's only one neighbor to Atlanta is Houston, so this is going to do only once, and then the vertex queue is empty because we will DQ it down. Do what? Do create a new flight from where? From Atlanta to Houston. So this is going to be plus the mean distance 600. You get the wage, and then you create a new flight from Atlanta to Houston with a new distance, which is 600 plus 800 is 1400. And then you go back, right? When you DQ, it's going to DQ the priority queue. This is a priority queue. It's looking at Washington Dallas is going to come out first. Let's print that out. And then look at the neighbors of all the Dallas. Right. We look at priority queue, and all Dallas neighbors going to get in queue first again, which is Denver and Austin, right? And Chicago too. So it's keep doing that the same. create a new flight, accumulating it, and then start to print them all out. So that's why you have DQ, the priority queue, Atlanta, Houston out first. We look at the distance. We say the shortest is going to go first as a priority. So that's why this just do from less to max distance. And then we get this shortest path. And we already see it being implemented. Okay, so that's the algorithms, and that's how we implement it. And let's talk about unreachable vertices. It said with this new graph, we cannot fly from Washington to Austin, Chicago, or Denver. To print unreachable vertices, append the following to the shortest path. The unreachable vertices are vertex equals to graph dot get unmarked, while vertex not equals to null. Then you print vertex and then mark vertex, and then graph that get unmarked equals to vertex. So let's look at the code. You pretty much just, so after we are done, right, the queue is empty, then we pretty much just get this table print out, and then we're going to say the unreachable vertices are, it's going to keep printing out, like get the one that unmarked, because we didn't mark them, right? So we're going to mark them all, as long as not equals to null, right? So while vertex not equal to null, right, we mark as we visit. Okay. Unreachable vertices pretty much just, you can fly from Washington to Austin directly. You have to go to Atlanta, right? Actually, you can't go to Austin at all because there's no path to reach Atlanta, Houston. You can't go to Austin. There's no flight to Austin, even if it's connected. You can't go to from Washington to, I mean, the top of this is different graph, right? The one before, let's check. The one before we have Dallas connected, right? So that's why we could go to Chicago, could go to Denver. So if there's no 1,300 here, then this is just unreachable. You can't go to Dallas because there's no connect path. You can't go to Denver when we cut that path out. Okay, so again, to print that, get unmarked vertex. While it's not equal to null, just print. Keep doing that until vertex is equal to null. Right, because you keep getting unmarked. Pretty much just get all the unmarked or unvisited vertices and print all the information about vertex and mark as visit. And then it's pretty much just print the list of here unreachable vertices. If in the case that the graph has been changed, right? Or sometimes you may see you create a constant graph.